only hear the best. You have to understand that. And that is one of the exactly the best. Unfortunately, Albert Fert, you have to know that unfortunately he's sick, he cannot come. The 16, 17 years ago, I created the Spintronic conference in United States, in SPIE. I invited Albert Fert. He came, he gave the talk. I mentioned that you are going to have the Nobel Prize, and that he got 2 years later, and he had a lot of results that unfortunately, but we have the best. Okay, sir, please.
Well, thank you very much, Manijay, for this splendid introductions. And myself, I'm also a passionate person, you know, I like passion. And what I'm likely to talk to you is about my passion for extreme light. And extreme light is not, I mean, you took a lot, of course, you know, you showed us a lot of your beautiful results, you know, on power production, high power production, lasers and so on. I'm going to do the same, okay? But you will see the different scales. But I'm, the type of light I like to produce is very short and very intense because it's very short. And it's always a pleasure when I talk, I give a talk to show my co-laureate, you know, Donna Strickland. Okay, so thank you anyway for this invitation, Manijay. Okay, so I'm trying to do my best, but after you, it's very difficult. So I'm going to talk about extreme light. And why extreme light? Extreme light is high, light of high intensity, is exciting because it is now can provide the largest peak power, of course, the largest temperature, the largest pressure, the largest accelerations, the largest field. In fact, we are come close to the trigger limits, you know, very, very close to the critical field. Not, I shouldn't say not very, very close, but we are not very far from the critical field. And with this extreme light is really a universal source of high energy particles and radiations. So, of course, we have before we talked about laser light. Of course, everything started with this gentleman, Ted Neyman, 60 years ago. And laser is 60. And what's phenomenal, what I like about the laser, is that you can use this EV light, because it was, at that time, it was EV light, to slow down atoms, right? And of course that open up the field of atom cooling and so on. But the other thing that you can do just, I mean, so you can slow down atom almost to rest, right? And the other thing you can do is you can accelerate particles close to the speed of light. I mean, in fact, very, very close to the speed, with large load factor. And so this is what turns me on about lasers. You can really go from, with one EV light, you can really cover a range of 24 order of magnitude. You can go to the PEV, pico EV, to the GEV. I'm sure one day we'll see. So one thing is, first of all, we can easily produce petawatt. And a petawatt, of course, 10 to the 6 gigawatt, which is 1 million nuclear power plants. But of course, for fantasy. But then, nevertheless, it's amazing. And but also, if you take this petawatt and you put this petawatt over a spot size limited by diffraction light, micrometers or so, you can produce light pressures, ponderometric pressure, enormous, okay, which correspond to, let's say, about 10 million Eiffel Towers on the tip of your finger. You know? So this is high pressure. Right? And you do that with light. This is what's nice. So now, since 1960, when the laser was invented, this is really the diagram of focus intensity as a function of years. We started in 1960, and the laser was offering already powerful light. You know, it was a intensity, very high intensity light. So power over area. And but at that time, you know, about 10 to the 8 watt per square centimeters was very good. And then Q switching, locking came along, but also we were reaching very quickly new intensity range. But at that time we hit a snag. I mean, we couldn't really go over because the nonlinear effect in materials, well, they were preventing to go higher than 10 to the 12, so watt per square centimeters. And this is what we came with Donna, which is this idea of compact CPA, a CPA, which was a technique to circumvent the problems of nonlinear effect that we were preventing. And the CPA, we'll see that later on, but this is used. Everybody knows it, this audience, what it is. And so I would, but I just like to, so of course it was exciting because immediately we could go into new territory. And the first things that new things was relativistic optics. You know, at 10 to the 18 watt per square centimeters, the laser field is really so large that it can drive the electrons which are normally going at a very low velocity when it jiggles around the nucleus. But here, the electrons is going at the speed of light. So you have now to take into account the V cross B that you are producing. And so now it's a new kind of optics and so on. And one thing you can really do with this V cross B, of course, is try to accelerate particle, and you will see that you can do that very efficiently. Then when if we keep accelerating, if we keep increasing the intensity, then we go into this ultra-relativistic optics that I call is not because relativistic optics because the electron, we are jiggling the electrons at the speed of light, but ultra-relativistic optics is because now we are able really to move the protons, at the velocity of light. That also, it opens up, completely novel area. And here we are coming also, when we push even higher, we are not here yet, but we are coming, okay? We are coming to intensity where we are materializing light, materializing vacuum, okay? We are coming to the point where we are breaking down the vacuum. Okay? This is happening at the Schwinger level, which is when the field of the laser is the field is reached a critical value, which is field which is 10 to the 18 volt per meter. It's a critical field. So, and we are coming to that field, okay? And so that is very, very exciting. So now optics is really gives us the capability to do so many things, which is amazing. So in order to go, and I'm going to talk about our voyage, to go at the Schwinger limit and beyond. So I'm going to describe applications in this yellow band. And so, of course, in order to get very, very high intensity, as I mentioned, or high power, we are not going to increase the energy, okay, because power is energy divided by time. But we are going to decrease. With a relatively small amount of energy, we are going to decrease pulse durations, because the cost of a system is proportional to the cost of the energy, okay? Not the function of the pulse durations. So here, we like really to go as short as possible. Now the pulses that we are producing is typically in a few femtoseconds, which means few optical cycles in the visible. Okay? And so the pulses are in 20 femtosecond pulse is composed in fact of 10 optical cycles, of the order of 10 optical cycles. And then we like really to go much shorter than that. And so first, we like to go to the single cycle limit, and that will take us to the femtosecond level. It's not enough. We like to go faster. We like to go shorter. And I will show you how we do that to go shorter. Okay, so first, to go to the single cycle, we use the fact that the index of refraction is a function of the intensity. And that means it's a function of time. And so we can produce, because if we want to go shorter, of course, what we have to do is we have to broaden the laser spectrum. And to do that, we are using the cell phase concept of cell phase modulation due to the fact that the index of refraction is a function of time, because it's a function of the intensity, and the intensity is a function of time. And so this way, we can really broaden easily the spectrum of the laser, and after that, by using a pair of dispersive elements, we can compress the pulse. Now, we are at the femtosecond level, because we are, as I said, we have just compressed the pulse to a single cycle. but we like to go shorter, right? Much shorter. Okay. How can we do that? Well, to do that, right now we are exploring the concept of relativistic compression. That is, we are going to try to make a mirror which is going to move at the speed of light. Okay? And by doing that, you know, you can in fact compress the pulse by the Lorentz factor of your moving mirror. So how do we do that? So we are using, as I said, we have just produced by cell-phase modulations, we have produced a single optical cycle, okay, of high intensity, of course, very, very high intensity. And we are going to, or high power, and we are going to focus this single cycle on on a specimen composed, of course, of electrons and protons and so on. So this single cycle at high intensity is going really to ionize, of course, the medium, and it's going to push forward the electrons. Okay. So the electrons are going to be moved forward, and the ions which are more massive are going to stay behind. So we are going to generate a very, very large space charge, which is going to lead to a very large field, okay, quasi static field, and this field is going really now to attract, to move the electrons, because it's huge, back forward at the speed of light. So you have a system where you have the light coming at the speed of light, and the mirror coming at the speed of light, hitting the mirror coming at the speed of light. So you can show easily that you are, in fact, going to compress the light. Very much like when you are, if you are, on the beach and you see the wave coming, and if you have a scoop and you try to scoop the water, and you are going, and if the velocity of the scoop is of the order of incoming light, you are going to compress the wave. Okay? Anyway, so this is the way. So when we, I'm going to go not too much in details, but so this is what you get. In fact, you can compress the light pulse by the pulse duration will be compressed by a factor of 600 over A naught. A naught is a normalized vector potential, okay? And it can go to A naught power 1 or A naught power 2. So now if I have the field, A naught, as I said, normalized vector potential, so if I have the A naught on the axis, 1, 10, and so on, you see that you can really go, you can compress, so you are expecting to compress the pulse by a factor of 10, 100,000 and maybe higher. And in simulations, for very large A naught of 10 to the 3 from 100,000, which corresponds to intensity at 10 to the 22 or so watt per square centimeter, something that we can do down. We should be able to get pulses in a Z-to-second regime. Okay. And Z-to-second is is of course 10 minus 21 second. And also, is something, 10 minus 1 second, is also the period of gamma ray pulses, okay? Gamma ray light. So you see, you can produce a very short pulse, and in a gamma ray regime, you know, X-ray gamma ray regime, which is, of course, very exciting, because this type of pulse, first of all, let's suppose that you have 1 joule in 1 zeptosecond, then you have 10 minus, you have a zeta watt system, okay? But also, what is nice, as I said, is this is a coherent. The burst is a burst of coherent light. And so that is, of course, very, very exciting. And you would see that will be the burst of light, a very high intensity light, and you will see what we can do it in terms, if we wanted to accelerate particles. So, in fact, so with this zeta watt, if you take a zeta watt, you know, and you focus over a spot, lambda square, the spot, of course, of a gamma, doesn't have to be a gamma wavelength, but you can easily get into the Schwinger densities where we would like it to be. So, and then you turn light into matter and antimatter. Now, I'm going to come back. We'll see what we can do. A very important application of this zeptosecond. Even if it's not zeptosecond, but it is maybe 100 zeptosecond, it's going to be very exciting. Now, one of applications of very high intensity is the fact that we can accelerate very efficiently particles. And we can use a scheme, concept, which was really put forward by Toshi Tajima, good friend, and which is really works like a surfer on a wave, where now the electrons are going to be pushed by a plasma wave and very efficiently, as I mentioned, as a surfer on a wave. So now we are coming back from the gamma ray regime, we're going back to the visible regime. And so, as I said, if you can produce this very high intensity, okay, pulse, you can focus this beam on the plasma, on the gas jet. We are going to create a plasma, and now. Plasma and a plasma wave, and you are going to have electrons dropping in the plasma wave, and this plasma wave is going to drag the electron forward at the speed of light. And what is very amazing is, of course, these electrons are going to be dragged at the speed of light. And and you are going to produce very high energy beam, okay? And the acceleration gradient is phenomenal. It's in a regime of GeV per centimeter. That is, you will be able to accelerate electrons to the GeV level over 1 centimeter. This, of course, is phenomenal, because we know how to accelerate or how to produce electrons, to the GeV. You have a solid, yes, what you do. But this synchrotron is kilometers in circumference. Okay. So now we can do it, and we can do it. I think we have done up to 10 GeV. So of course there are extremely compact systems. So this shows, of course, the advantage of laser accelerations. So, but this is with the visible. Now let's suppose that we can produce our X-rays, gamma rays, and the acceleration that we can get goes with the square root of the electron density. Okay, so when we are using a gas jet, the electron density is 10 to the 18 or so. So we get something like 10 to the 9 GeV per centimeter. That means, GeV per 10 to the 9 GeV, 10 to the 9. Okay, so it's a GeV per centimeter. Okay, but now, I just showed you that we should be able to produce very high intensity bursts of X-rays or even gamma rays. So we can use solids at 10 with density of 10 to the 24. So electron per cubic centimeters, which means that we should be able to produce teravolt per centimeter. We order we move from GeV we will move from GeV per centimeter to the TeV per centimeter. So the teravolt is CERN. Okay, right now laser particle acceleration at the TeV level. This is what people are doing at CERN, and they are using radio frequency, gigahertz frequencies, and it takes 20. The ring, the accelerator ring is 27 kilometers circumference. Okay. So and now if you are using the lasers, visible light. Okay, so we go from 10 to the 9 Hertz GeV frequency for the microwave. We move to the 10 to the 14th. We can huge factors. Goes with the square root of that. So now we can go into we take now this TeV and we can produce it over 100 meters. But if we have now X-rays, we should be able to do it over a centimeter. Okay. So of course this is now there's one thing that we can also we can accelerate electrons, but we can also accelerate protons, and we can produce protons. We should be able to produce proton at the GeV level. GeV protons are, of course, relativistic protons. And it's very easy. We focus, if we can get it, we have a thin specimen, nanometers in thickness, and we shine the light. And so because of the really very, very large ponderomotive pressures, we can push the electron forwards. And the ions heavier stay behind. But you are going to have the electrons which are going to attract, like a horse, carbon horse, pull the protons, and the proton we can see, and what we can get, we can really with single cycle, and single cycle works better. Yeah. Here we see with single cycle, this is also red. You know, we can get GEV pulses easily with relatively with field that we can produce. Okay. And that is very, very exciting. And you know, if you want really, you see that we could really produce GeV protons now. I mean, we are, and we will be able to do GeV protons. And GeV protons, you want to produce GeV protons in a conventional way, it takes, of course, the linear accelerators, which is about 1 kilometer to 500 meters long. And, you know, will be extremely expensive, of course. They are extremely expensive. So if you have these protons, what's exciting, if you have these protons, then you can really, by spalations on heavy metal also, we can produce neutrons. Okay? At a rate of about neutrons for 30 MeV. So if you have GeV, you produce protons, 30 protons per neutrons, per proton. No, produce 30 neutrons per protons. Okay. So this is, of course, is very, very important because there's a lot of application you can do with protons, and I'm going to go over some of the applications. But now we can do, first of all, we can use these protons for cosmology, or X-rays, gamma ray for cosmology. We can really basically, we can simulate now. In fact, with our laser, we could simulate, you know, gamma ray burst, right? And on the table, and we could really study things like Lorentz invariance and so on. Right now, to study with gamma ray burst, to study Lorentz invariance, knowing that the gamma ray burst is about minutes in duration also. In order to see any effect, you have to really to have a very long base, you know, which is about 1 million years. Okay, then you start to have effect on the, if you want to see Lorentz invariance and so on. But if you can produce this gamma ray burst with the type of laser we have, where the pulse would be in a zeptosecond scale, then of course you don't need to, the target doesn't have to be at 1 million years, you know, away, okay, but it could be done on a kilometer bench of about 100 meter or kilometer bench, so it's very exciting. Also, the fact that we can produce particles at the speed of light in extremely short time scale, okay, in a femtosecond, okay, which means that the acceleration are humongous, okay, so accelerations of 10 to the 25 G, or something like that. And of course, if you use the equivalence principle, Einstein equivalence principle, then you will be able really to create analog of black holes. Very easily in the laboratories. A black hole of million size, something like this. So that is another very exciting applications, of high extreme light. Now, of course, you have very important application in medicine. As mentioned, that we know how to produce protons. We should be able already to produce protons, now in a GED, and you would be able really to produce, to do things like proton therapy with very, very compact laser system. I showed you, but we can produce. You should be able to use GeV protons, over very compact, tens of meter size systems, and so we could do proton therapy. Proton therapy is very, very important because, as opposed to X-ray therapy or electron therapy, X-ray therapy or gamma electron therapy, the damage. If you focus the beam on the tumor, you are going to damage the tissues, which is around the tumor, and which is not the case on the protons, where with the protons, you can really focus the beam on the Bragg, because the protons, propagate, deposit this energy at the Bragg point, and the Bragg point is something that you can adjust with the energy, and so you leave most of the tissues unaffected by the therapy. And you can also do many other things, radionuclide and so on. The fact that we can produce neutrons and so on, we can use it in nuclear energy productions. Okay. That we have the neutrons, we can produce the neutrons with the lasers. And then you can do, of course, you can produce energy by just being fission, okay? And so that will be, if we can come up with a very, and that's what we are trying to do now, to a very cheap source and efficient source of neutrons, and we can produce energy. The other thing you can do, of course, is really trying to do transmutations of nuclear waste, because when you are really shining the laser on your neutrons, some of the neutrons on nucleus, some of the neutrons are going to be trapped in the nucleus, and is going to make some transuranium elements, which are the bad stuff, okay, which are this waste, has a very long life. Millions, thousand years, million years, also lifetime. So, but with neutron we can take we can take this nuclear waste okay, from the Neptunium also, which is 2 million years. And then we can use and we can fission the material in smaller elements. And this is what we call transmutation. It would be very nice if we could do it in a way, if we had a very efficient neutron sources. And this is what we are trying to do with the laser. Trying to do transmutation of nuclear waste. Okay, I'm going to now to end here. And we were with Donna when we got Nobel Prize. We were invited by the Pope. Okay, and so we say, well, what are you going to say there to Pope? Okay. And of course, what we told the Pope was all the applications, and particularly applications about nuclear application and about the possibility of producing energy in a very clean and efficient way. And he was really happy about that, glad to hear that. So now I'm going to conclude by saying that extreme light is capable of generating the largest field, the largest acceleration, the largest temperature, the largest pressure, and it carries the best hope and opportunity for the future of science and technology. Very, very much that is in the spirit of the Nobel motto. Okay, thank you very much.
Fascinating talk. And you demonstrated exactly the things that I was saying. No, you went. No, you deserve Nobel Prize. And it's fantastic. It's impossible, the things that you did. And it's very, very, very important. So that really is great. I don't know what can I say. But if there is any question that is really a kind of inspiration, and you went very far, it means that up to gamma ray. Because I was speaking about that, because if you listen to my TED talk, I'm telling that. Okay, that is exactly the things that we are expecting,